the mean value theorem for integrals and the average value of a function. So yeah, there is a mean value theorem for integrals. I'll give it to you. I'm just going to state it, and then I'll show you a picture that will make you believe it, I bet. And the statement is this. There exists, for a continuous function f, there exists a c. Okay, this is weird notation. So this is a number. For any particular problem, this is going to be a number. And this symbolism means element of. So for a continuous function f, there exists a number c that's an element of the interval from a to b, such that dun, 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 the integral from a to b of f of x dx is equal to f of c times the quantity b minus a. So if you just look at this symbolically, it looks weird, and you wonder, well, where did this come from? But if you think about what c has to be, or what it really represents, then and if f is continuous, then it makes total sense. So here's the picture. F is a nice continuous function. Happens to be increasing. That doesn't matter. But for the interpretation, it is important. For the picture that I'm drawing and the interpretation we're going to think of here, it is important that f is greater than 0. So what are we saying here? We're really thinking of f of c as the average height of f over the interval from a to b, assuming it's an integral with respect to x. So average height of f on the interval a to b. And when you think of it that way, what we're really saying is there is a c value in between a and b. I don't know what it is. I'm just going to guess at it. I don't know if I'll be right. I'll say right here is c, such that when you plug in c into the function, of course, that takes you up to this height onto the curve right here. And if you think about what f of c times b minus a represents, it's really the area of a rectangle with sides of length b minus a. So that would be the length of this bottom side. And the height is f of c. So what we're really saying, that what the mean value theorem is really saying, is there's a c in the interval such that the area formed by this rectangle is the same as the area underneath the curve. And that should be intuitively clear to you. There should be, if f is continuous and if f is positive, because if we're not talking about a positive f, then we're not necessarily talking about an area for the integral, right? But it should be intuitively obvious then that there should be a c in between a and b such that I can get a rectangle with one side the same length as the interval a to b, and one height value f of c such that that area in green is the same as the total area underneath the curve and above the x-axis. Does that seem reasonable? And then we think of that f of c as being the average height of f on a to b. Okay? So that's it. That's the mean value theorem. And then if you solve the mean value theorem for f of c, you get a formula for the average value of f. You know, solving that formula above for f of c. So the f of c, that f average is f of c, and the idea is you're just solving this formula, dividing both sides by b minus a, and you're getting this formula. So the average value of f on the interval a to b is given by 1 divided by b minus a times the interval a to b f of x dx. And here's another function, another picture of another positive continuous function on the interval from a to b to help you understand these ideas. Now, think of f as kind of this jagged hilltop here. For some reason, it's really flat right there, but it's just, I've made it this way for ease of demonstration of the theorem. So basically what the mean value theorem for integrals says is that for a continuous function on the interval from a to b, there should be a c in that interval from a to b such that f of c is the average height value of this jagged hilltop on the interval from a to b. It's the average value of the function. F of c is the average value of the function on the interval from a to b. And what that means is, in terms of our area in green here, I can take the triangular region, the area of the triangular region above f of c, and use it to fill in these sunken in regions exactly to come up with that rectangle that has the same area as the area underneath the original function and above the x-axis in that interval from a to b. So the idea is you can cut off this top part of the hill and use it to fill in these valleys. This will create a mesa, a flattened hilltop, and the resulting rectangular region will have the same area as what was originally underneath f from a to b. If you buy that, then let's do basically one example with 3 parts, and that's it for this section. So the function is f of x equals 4 minus x squared, and we first want to find f average where a equals 0 and b equals 2. So what's the formula for the generic formula for f average? Yeah, it's just the integral times 1 over b minus a. It's not too hard to remember. So it's the integral a to b, f of x dx times 1 over b minus a. That's what we're saying the average is. So we just need to apply this formula to the given information. Well, the given information is that f of x is equal to 4 minus x squared, a equals 0, b equals 2. So fill it in for me. It would be 1 over b minus a, 2 minus 0, or just 2. Integral from 0 to 2, 4 minus x squared dx. All right. Make sense? Let's evaluate it. Help me out here. What do you get when you take the antiderivative? 4x minus, whoops, x cubed over 3. Evaluated from 0 to 2. What does that give us? 1/2. 8 minus 8/3, and then everything zeroes out when you plug in the bottom limit. So what is that inside the brackets? Yeah, so 1/2 times 16/3, or 8/3. Okay, that would be, you could think of that as the average height of the function over the interval from a to b. Okay? 8/3. Now in part B, you're asked to find C such that f average is equal to f of c. You're asked to find that c value. Okay, any ideas? So the idea is f of c, f of c is, using the function notation, f of c is 4 minus c squared, isn't it? So if f of x is 4 minus x squared, f of c is 4 minus c squared, isn't it? Just playing with the, what the function notation means, substitution. And then the idea would be, well, let's set that equal to whatever we got for f average. So that would be 4 minus c squared is equal to 4 minus c squared is equal to 8/3. And so we solve this little equation. Add c squared to both sides and subtract 8/3. Does that make sense? So I'd get c squared is equal to what? 4 minus 8/3. Okay, so 4 is really, what, 12/3? So what do we get for c squared? 4/3. Okay, so what's c equal to? So 2 over root 3. However, well, okay, normally you would put in a plus or minus, right? Why don't we need both of those? Yeah, we're in the interval. In this case, we're in the interval from 0 to 2. So we'll throw out the negative because it's the negative root is not negative 2 over root 3 is not in the interval. So the only c we're going to take then is c equals 2 over root 3 for part B. Okay, so the idea is if you plug in 2 over root 3 into f, then that height value is the average height of the function over the interval 0 to 2. So then part C says sketch the function f and the rectangle whose area is the same as the integral from a to b f of x dx. Okay, where f is 4 minus x squared and a is 0, b is 2. Okay, so we're going to put it all together. The mean value theorem, the average value idea, all in one nice, neat picture. So let's sketch f. So what's the vertex on that parabola? Okay, so 1, 2, 3, 4. We don't need the whole thing, but we'll start out with the whole thing. What are the x-intercepts? 2 and -2. So, you know, let me do this just to give it a little more space. Let's do this. Okay, so there's your vertex, and then the x-intercepts are at -2 and +2. And so normally you'd graph a parabola that looks something like this. But really, what part are we interested in? Just the part that goes from 0 to 2, right? Okay. Now, what value is, numerically, what value is 2 over root 3? So root 3, I think, is like 1 point something, but just do me a favor. On your calculator, take 2 divided by root 3. Give me the answer accurate to one place past the decimal. What do you get? 1.2? Okay. So that's the best I can do there. So 1 point, I'm going to go over, to 1.2. 1.5 is right about there. 1.2, I don't know, somewhere in there. And then I'm going to just go up to the curve. And this is, I'm just eyeballing it. It's not going to be all that accurate. Go up to the curve, and then draw in the rectangle with base that goes from 0 to 2. And the height is f of c, where c is whatever it was, 2 over root 3, I guess. Okay, so the idea is that this height right here is f of that c value that we just found. Okay, and then this value that I plugged in right there is 2 over root 3. Okay? And that's supposed to be a rectangle, although I got a little off when I drew it freehand, which is fine. Okay? guess what? That's it for this section.